All right, I think we should get started.
Okay.
So it's a great pleasure to introduce Jeff Eldredge from UCLA. Jeff is a professor in mechanical and aerospace engineering and currently also department head at UCLA. Before that, he did his PhD at Caltech and a postdoc in Cambridge, across the pond. Yeah, Jeff won many awards. He won an NSF Career Award. He won a UCLA Teaching Award. He's associate fellow of AIAA. He's fellow of APS. He's a sort of a standard in the giant in the field of unsteady aerodynamics and reduced order modeling. I've been lucky to have known him for many years, and it's a pleasure to sort of follow the work and try to meet that standard. Over the last sort of 5, maybe 10 years, he's been taking that knowledge of reduced order modeling in unsteady aerodynamics and applying it to data-driven methods and reinforcement learning. And so today he's going to show us some of his recent work on that.
That was a very, thank you. It was a very kind introduction, Wim.
Thanks for being here.
I want to thank you for inviting me. It's truly an honor to be here. So I'm going to tell you a little bit about the things that have been on my mind for the last couple of years. And and as you mentioned, I spent most of my career thinking about vortex modeling of flows. I like vortex elements as sort of small scale elements. Elements that can help us reproduce flow fields, with some physical intuition, but I've moved away from them in sort of a grudging way. And so you'll sort of see the fracture line in this talk about where that went. Okay. So I find myself working on all kinds of different things over my career. And notice like a really weird one in here, bacterial mechanics, which I got into about 5 or 6 years ago through sort of happenstance, which has been a really interesting sort of side venture that I work with some physicists on. But I'm not going to talk about that today. I'm going to talk about these first 2 topics that sort of go together. One is an outcropping of my old work on bio-inspired locomotion in fluids, which I was fascinated for by many years. And that sort of morphed into aerodynamics of agile flight. So just flying things or wind turbines or things that are basically subjected to disturbances, exogenous disturbances in the atmosphere, or their other vehicles. Okay. So this is work that's been carried out by a number of people in my group. Some of you actually might recognize the first name, which is Matthew Le Prevost, who sadly passed away and is a huge loss for our community. Matthew was just a shining light in this area, and I miss him dearly. Diederik Beckers was another student of mine who's a postdoc now at Caltech, and the 2 current students working on this are Hanya and Zhecheng, and they're both their fingerprints are on the things we'll be talking about today. So this is actually kind of a motivating slide for some of the things we're interested in. This is a review paper from my friend Anya Jones, written a few years ago, where she just imagined all the different areas where there's disturbances in the atmosphere, and things that are flying would have to be subject to it, or also wind turbines. You see there, wind turbines can create their own disturbances for themselves, but also for other things flying nearby. Ship wakes are a place also where things that landing on aircraft carriers need to be worried about this. So there's all kinds of places that there's disturbances in the atmosphere that we need to be concerned with. And as vehicles become smaller and lighter, then they are more prone to being disturbed by those gusts. Okay, so they become larger amplitude relative to their weight. And that might require large amplitude actuation to address that, to mitigate those disturbances. So it means that things like linear control, which have been a sort of bedrock for control in lots of areas in flight mechanics for many years, they may not be as effective anymore. And it also might mean that we need to know more about the flow field than we used to need. It used to be that we could just rely on the pretty simple sensors on a wing, like the inertial measurement unit and so on, to detect disturbances. And now maybe we need more aerodynamic sensors. Okay. So motivating problem I'll talk about is a very simple sort of toy problem that we've been thinking about for a while. And then I'm going to go from this motivating problem into just a little bit of background. Some of you will know this very well and undoubtedly better than me in many cases, given who I'm talking with here. And so we'll show some examples where we've been applying data assimilation to aerodynamic flows. So a lot of that will be where we progressed in addressing flow estimation. And then I'll talk about reinforcement learning control, okay? And so let me first show this motivating problem, and I'll talk about how these ideas might fit together, okay? So this is the simplest aerodynamic shape you can imagine. It's a flat plate, okay? It's not an airfoil, it's just a flat plate. And I have this wing, I'll call it a wing generously, okay? It has a pitch control. It's got some sensors on it, these little pressure sensors, and it's going to be responding to these gusts form vortex dipoles that are hitting it from different directions and so on, different strengths. And the goal is to basically make the lift as close to zero as possible, okay? A very simple control objective, not necessarily one that we would need to do practically, but it's a very simple one to start with. And it reveals a lot of information about what we can do. So the idea is we have these sensors on the wing, and that's all we have available to us to tell us about what this gust is doing, okay? So all the signatures of that gust are in there, okay? So the disturbances might come in sequences as well. So there might be more than one. In fact, that's going to be an interesting problem. The gusts are strong, so their strength is significant compared to the natural flow scales on the wing. So we just have one actuator to worry about to address that. So the way reinforcement learning sort of addresses this problem is to think about that whole problem, the environment is just a big black box here, right? Literally a black box where you put actions in, okay? You take observations from that environment, limited information you have, and rewards, some definition basically of like what's good, okay? And those things go into an agent, and the agent has to make a decision on what to do next as an action, okay? The action in this case is pitch control, okay? And so that agent is the sort of thing that we need to train. We need to find a policy where it takes the current state of the system and chooses it as an action. That's the whole idea of the agent. And it can do that also in a probabilistic manner too, but that's the basic idea. Okay, so one of the underlying problems is that we actually don't have the full state in fluid dynamics. Fluid dynamics is well known to be partially observable, right? So we just have sensors. The sensors are just telling us some partial information about the flow field, but not the full flow state. And it's not clear how much of the full flow state. The full flow state is the entire velocity field and pressure field, right? That's a lot of information. Maybe I don't need to know all that stuff to make good decisions, right? So there's an underlying question like, how much do I need? So how do we go from limited observations, which in our case will be pressure sensors, to some state that I have enough information to make a good control decision on, okay? So that's one of the things that'll color what we do. Now, in our case, the black box that's here is going to be CFD, all right? So I'm not going to show any experimental results here, but that's always the eventual focus is to do things obviously in a real system. But here we're just going to create disturbances in this CFD sort of environment, and then that can spit out a reward function, something about the lift, and it'll produce the observations, which will be the pressure that I have on sensors, okay? Okay, so the central questions that I'll be reporting on here will be, the first one is about flow estimation. So how do I take sparse measurements on a wing? In this case, it actually is a wing, it's a NACA airfoil. And take that information and infer the flow state. And here I mean the entire flow field if possible, velocity and pressure and so on, or vorticity. And it's uncertainty. I want to know how certain I am about that flow field, right? Which is always an important question. And then the second question is about control. Like how do I take sparse measurements with a flow actuator and learn by experience to control the flow, right? So I always thought about these questions as like I have to answer one and then answer the next one, and sort of thought of them sort of sequentially. I always thought about this part as being embedded in this part, which it is. But because I have two students working on them, they do their own thing, and they came up with very good answers to their questions. And it turns out they don't even need to talk to each other that much, which was a little bit alarming. So I will show basically that Zheng came up with some solutions on this that didn't rely as much on our flow estimation as I thought, which is fine, but it leaves some things to keep working on. Okay, so I'm going to give you a little background on fluid dynamics estimation. or just estimation in general, okay? So we're going to focus on the necessary ingredients of most filtering architectures. One is some forecast operator that forecasts the next states from the previous one, and an observation operator, okay, where basically we take the state and it produces a prediction of what we think the measurement should be. So I provide a sort of a table of different examples here of states and in fluid dynamics. The most obvious one is the whole flow field, okay? And the forecast operator would just be one time step of Navier-Stokes, so we just march it forward. And the pressure comes from a solution of the pressure Poisson equation at sensor locations, right? So that's quite a bit of information. We're going to try to do something in a little bit more reduced order. So I mentioned that I like vortex flows and vortex elements. So one would be just a bunch of vortices in the flow, and I march them forward with the vortex dynamics, and then I can get pressure very easily from, say, Bernoulli equation. Okay, so that's another way I could do this. And the other one that I'll focus quite a bit of attention on is on a more sort of data-driven approach, where I find a very low dimensional latent state by using some machine learning tools. And I get the forecast and observation operators from other machine learning architectures. Okay, so that proves to be a much more effective approach, but slightly less intuitive, interpretable. Okay, so we'll talk about that. Excuse me. So I'm going to focus a little attention on this observation operator, because it's an important part of this whole thing. And I want to color this in the sort of fluid dynamics arena. So when you think about this state, I want you to think about a flow field, and I want you to think about Y as being, say, pressure, okay? And so there's a couple goals we might have here. The first goal is kind of a naive goal, which is to say, I really want the inverse of that, okay? So if I had the pressure information, what is the flow field? I kind of want to invert it, right? But that sounds kind of problematic, right? I have a few pieces of information here and there from pressure sensors, and I want to invert this to find the flow field. I think your gut instinct is that that's probably not invertible, right? There's too many possible answers, and that is often right. So we want to understand that inversion, or so to speak, better, and what that means. And of course, we'll express this a little differently in a moment, but it seems kind of ill-posed, right? The other part is that I may not know what H is. So H might be something I know from, say, physics, but it might also be something that I actually need to learn. Okay, so then there's a companion sort of regression process going on here, where I'm going to use them and then perform the inversion process with that. Okay, so all these things kind of go together. Okay, so we're going to do this in a probabilistic manner, because it actually gives us a lot better insight about what we mean by invertible, okay? Because we're not really going to invert things. We're going to find the most probable states, right? So the idea is that given some measurements Y, then what is the most probable flow state? Or maybe flow states, maybe there's more than one, right? So maybe this probability density here has a few different, peaks in it, right? So I'm going to treat everything as random variables, because it actually helps us do that. So these sensors are noisy, okay? And that means that X itself is also, uncertain, right? There's randomness in there. Okay, so we're going to take, this is our goal. We want to find that probability distribution. And so if I have that, then I actually have all the information I could possibly want. Getting this conditional probability here is basically, that's the whole thing, right? Because I can use that then and compute expectations of other quantities. Lift, for example, on a wing, okay? Or I could get other things that I need from a practical standpoint. So this is our whole goal. I can compute everything from that. And so, most of you here know about Bayes' theorem, so I'll just remind you about it. Bayes' theorem is a very principled way of getting at this conditional probability, because I can start with some prior distribution that I know, from prior knowledge, okay? Some idea about what my probable states are. And then I just march this through Bayes' theorem with a likelihood. This likelihood is much more sympathetic to what we have available to us, because it's the reverse of things, right? It says, if I know the flow state, what is my likely measurements, okay? And that's something I do know, right? So that's the sort of forward observation model that I showed you before. So if I know the flow state, I can tell you very precisely what I predict my measurements to be. So this is something we will have available either from physics or some other operator here. Okay, so the likelihood is easy. So Bayes' theorem is really nicely set up for this. And this thing in the denominator never really bothers us. We never need to know this thing. So really all we care about is that this is proportional, okay? So I have given flow states in here and a y star, which is some actual measurement we've taken with our sensors, then I can get this posterior distribution, x conditional on y star, and that's what I want. I want that thing, okay? So we can get this through a variety of different means. Some of them are sort of brute force Monte Carlo sort of approaches, but some will be a little bit more elegant too. Okay, so I'm just going to say a little bit more about that likelihood. I mentioned that likelihood is something we have available. So this observation operator here is something we know. We'll assume we know that observation operator. So I also know that if my noise here is Gaussian, which I'll generally assume that to be the case, so sensors are noisy with Gaussian noise, okay, we'll say, then the likelihood is also going to be a Gaussian about h of x, okay? Okay, so that's going to be advantageous. So I'm going to just quickly glance over the fact that if things are linear, then I can find the posterior distribution analytically, and this is obviously classical stuff here, very well known. But I'm reminding you of it because it's important to remember a few things about this. That if everything is linear and Gaussian, then I have analytical expressions for everything I want, a posterior mean and a posterior covariance that come from my prior, and it shows me everything I could possibly want. There's a lot of intuition buried in this, which is it's a very attractive way of looking at things. And the Kalman gain has this very nice, I write the Kalman gain in a particular way here, because what it's showing is it's balancing trust between what I knew before and what the sensors have now told me, right? So the sensors are noisy, then it's going to rely on what I knew before or vice versa, right? So if the prior is poor, like I'd start with like almost no knowledge of anything, right? Then this relies on the sensors and it basically just becomes a pseudo inverse here, okay? So it becomes very easy to deal with. If the measurements are poor, then I instead just rely on what I knew before. My prior becomes, oops, sorry. And my prior becomes everything. I just rely completely on the prior, and the measurement update is just ignored because my sensors are noisy or something, right? So there's two different extremes in there, and so it's usually somewhere in between, right? Okay, and then of course in fluid dynamics, it's almost never linear, unfortunately. So let's imagine, for example, the pressure depends non-linearly on velocity, right? So you could think of Bernoulli, P plus 1/2 rho v squared as a constant, right? So pressure and goes quadratically with velocity. And if my flow state is velocity, then pressure is going to depend non-linearly on that. And so that means that H is going to be a nonlinear operator, okay? And I need to deal with that, right? So one way would be I just do sort of a linearization about the prior mean, and that could work, okay? Or we do a brute force approach, I mentioned before, a Monte Carlo approach, where I just basically trial and error, right? And I use a MCMC, which is the sort of workhorse for that sort of approach, where you just keep trying new things and refining my probability. Okay, so I'm going to show you some examples of doing it that way. This is a nice problem that is easy to understand what we're trying to do here, and it's a nice way to reveal some of these tools in a fluid dynamics scenario. Okay, so these are just a few point vortices sitting out in space here. Okay, there's no surfaces here, just infinite space, and I've got a few pressure sensors sitting in this little arrangement here. And so I'm just going to take those pressure measurements, and I'm going to try to infer where these vortices are and how strong they are. All right, so each vortex, it's just two-dimensional, so every vortex has 3 pieces of information, right? An X position, a Y position, and a strength, okay? And the strength could be either sign, positive or negative. Okay, so that's my objective. So all I have are pressure measurements from these sensors and some noise, okay? They're noisy sensors. So this is my measurement vector, Y. I take those sensors relative to ambient pressure, and I'm trying to infer X, which is the positions and strengths. So that's how dimensional, that's the dimension of that, okay? All right, so your sort of naive view might be the intuitive thing to think is that I need as many sensors as I have pieces of state to estimate, right? So that's generally what we're going to find. So, and by the way, we can use Bernoulli here. It's very easy to find the pressure from these vortices. Right? So this is my observation operator. Okay, this is a Bernoulli equation. Okay, so I'm going to show you an example, a very simple one. I have 3 pressure sensors right there, and I have 1 vortex that I'm trying to estimate. So I have 3 pieces of information to find 3 flow states. That sounds like a nice balance there. And it turns out to be the case. I have some noise here, as you can see, a little bit noisy that my sensors are. Those are the pressures they got. And so when I do an MCMC sort of sampling of that posterior distribution, I get a range of possible values here. They're sort of clustered around there. And I'll reveal to you that the true location here, the true vortex location was there. So you can see there was some confusion about the Y location. In fact, that confusion is between the Y location and the strength, right? So moving it further away is roughly equivalent to making it weaker, right? So there's some confusion between those two. I don't show the strength on here, but so there's a third dimension there. Okay. So the expected vorticity field then can come from that. So that basically, now that we've got all those samples of the posterior, then we can compute things like expected vorticity fields and so on. So it does a good job of getting what we want. Okay, so that was easy. And so then you could ask obvious questions here, right? So one would be, let's add more sensors, right? So we'll add another sensor. Okay, what do we do? So we just tighten the uncertainty, right? So now we get a slightly tighter bound there. I can add 1 more sensor and get even tighter there, right? So it eventually we lose its diminishing returns. We don't do better and better forever, and it starts to taper off. I think I have one here. Yeah, so there's one where I put them in a ring. Okay, so that becomes pretty obvious at that point. But then what happens if I don't have enough sensors, right? Here's 2 sensors, and I'm still trying to get 3 pieces of information. So you can see that obviously there's a whole range of possibilities there that it doesn't know about, doesn't know any more than what it's given from these 2 sensors. And in fact, you can show that this is actually revealing a sort of helical manifold in the 3rd dimension as well. So remember, the 3rd dimension would be the strength of the vortex. So there's X and Y in strength. So this is what the helical manifold looks like in the 2-dimensional plane. It's just a circle, okay? The true vortex is there, but it doesn't know, it can't distinguish that from any other point on that helix, okay? So I can't do any better, right? So that's an obvious example of what we can't do, okay? But if I have enough sensors, I can infer these vortices. So here's examples where I have more than 1 vortex, okay? There's one here that's, I think it's positive, and this one's negative. Okay, so I'm able to distinguish those. There's 3 here. What's interesting actually is the nonlinearity of this problem actually helps you in a particular way. So one thing to keep in mind is that the pressure exerted by a vortex is invariant to the sign, right? So a positive vortex and negative vortex exert the same pressure, right? And that's a problem if there's only one of them, right? So I cheated on this one back here. I actually didn't tell you this, but I restricted my prior distribution to only positive vortices, okay? But it could have been negative, right? So I started my prior with a little bit of prior knowledge about things, and I said, oh, let's look at positive vortices. But here I did not, okay? And so it was able to detect that each one's relative sign to each other, and that's because of nonlinearity. There's some subtle nonlinearity that helps us out there. Okay, so that was kind of a neat little artifact of that they're not independent of each other. Okay, so nonlinearity can help and hurt, but it helped us here. Okay, all right, so that was a bunch of static estimation examples. Okay, those are ones that are nice toy problems, give you a little insight on estimation. But we are doing this with like literally one hand, it's not literally, figuratively one hand tied behind our back. Because we have not used previous information. Flow fields are usually unsteady that are interesting to us. So why can't we leverage past information to get the prediction, right? That's where sequential estimation comes in, right? So I'm going to now rely on the fact that I've been monitoring this state for a while with previous measurements, and I want to use that information to keep updating my estimate, right? So we're going to, rely on the, the nice features of nonlinear filtering to do that. Okay, so back to what I mentioned before, we have a dynamical model, okay, that can predict what the state's going to do next with a little bit of process noise thrown in there. And then we still have our observation model, just like before, that I can predict what the measurements will be, also with noise, okay? And so each of those has their probabilistic version, okay? So we already had the likelihood before, that's the same as before. But now we have this transition probability that basically is like, what's the probability of the next state given the previous one, okay? So those are the ingredients of a nonlinear filter, okay? So nonlinear filter is basically, you can literally do this analytically, but it is, you're not going to be able to do it analytically in a fluid dynamics problem because it's a huge sort of cursive dimensionality problem to advance these equations forward. So we never would work with these exact equations here. We have to do things in some sort of approximate way. Now, if it's linear and Gaussian, again, if linear and Gaussian, what are these equations? Anyone know what these equations become? Linear, what are the filtering equations reduced to when it's linear and Gaussian? Become a Kalman filter. Okay. I just wanted to see if, okay, so it's a Kalman filter. Okay, so the Kalman filter is the solution of the filtering equations for a linear and Gaussian model. All right, so the forecast model is there, analytical model is, analysis model is there. So I'm able to march forward my prediction of the state and my prediction of the uncertainty analytical, right? And so a Kalman filter is a sort of a beautiful piece of machinery that is exactly what we want, except that it requires it to be linear with Gaussian noise. Okay, so it's a little restrictive. Okay, so most things we do are some variation on a Kalman filter, right? And so there's lots of variations. There's extended Kalman filters and unscented Kalman filters and so on. We're quite fond of one that works well in the fluid dynamics context. It was actually produced really for meteorology originally, because so it works well for large dimensional systems. That's where filtering becomes challenging, is that you're trying to march forward this large dimensional state, and it's large dimensional covariance, right? So if you think the state is large, well, the covariance is large times large, right? That's a very big covariance matrix to try to update. So we want to do that in a cheaper way, and ensemble Kalman filters help us do that. So we go back to what we were doing with those Monte Carlo things and think about that a little bit, right? So ensembles, take an ensemble of different estimates of the state and march those forward. Then we can just take the statistics of that ensemble, and that becomes what we need for uncertainty quantification. Okay, so the ensemble is the thing that helps us out. So we just march things forward individually. Each ensemble member gets advanced in its forecast, and then the analysis step is just taking measurements in. Okay, so there's lots of different ways we could do that ensemble Kalman filter, but I'm going to highlight this one at the end that Yusuf and I and Matthew and Ricardo worked on a few years ago, and that's our favorite one. You know, we're biased, but actually no, there's no bias there. Sorry, that was a joke. So then this low rank Kalman filter unwraps this K matrix here, this Kalman gain, and it does so by making use of the gradient of the observation operator in different formats here. So by using this, I don't go into details here, but you can basically use spectral decompositions of these to figure out the different eigenspaces that in the measurement space and then the state space, and it finds the most informative directions in those respective spaces to carry out this Kalman update. Okay, and that's very useful because what it allows you to do is take the ones that were sort of lower, less informative, and throw them out. And that's very helpful because these ensembles tend to have lots of spurious correlations that you don't really want to deal with. And so this allows you then to basically dispense with the spurious stuff better, okay, in a very principled way. Okay, so that's our favorite way of doing things. And it's pretty cheap to do. And even when we talk about neural networks in a bit, gradients in neural networks are easy because we do that all the time when we train our neural networks. Okay. Okay. So I'm gonna this is the sort of fracture line where I say, okay, vortex-based estimation is great, and I love vortex flows, vortex elements, and so on. They're physically intuitive. The vortex states form a nice low-dimensional space that I can, reconstruct flow fields from. So I could use a lot of vortex elements to produce a flow field. Okay, that's fine. And with enough sensors, I showed that we could actually infer all the vortices. That's great. Okay, so it's nice and intuitive, but right, there's some really big drawbacks of it. The first one is I actually, like, if I want to estimate a whole big turbulent flow field, I don't know how many vortex elements would be the right number to use for that. So even the dimensionality of my state is kind of in question. Okay. And it's also an inviscid model, right? So we're actually just advancing vortices as an inviscid sort of model. You can, expand on that, but the idea is that these are two drawbacks that kind of get in the way of making this successful completely. So we've turned our attention to something different, okay? And so this brings us now into sort of machine learning world here. But a really elegant one that I'm actually become very fond of in a very short amount of time. So autoencoders are sort of a natural extension of an idea we've been using for many years in fluid mechanics. So we've often tried to compress our flow field into something very low dimensional. And so for many decades, it's been, say, POD, proper orthogonal decomposition, which is a way to find the most energetic modes in a flow field. This is the natural extension of POD in many ways, because it uses nonlinearity in these neural networks to encode the flow into a very low dimensional state and then decode it, to get the flow field back. Okay, so the only thing you really need to provide is an architecture here. You have to specify in advance what the dimension of that latent state is, right? So you actually have a little choice in the matter and a little bit of exploration to do. What we do is sort of extending the idea that was put forward by my friend Sam Taira and his student Kai Fukami, who's himself now a professor in Japan. So Kai and Sam realized that if they had an extra network attached to this that predicted lift, okay, then it would actually do a nice job of sort of organizing this latent space in a sort of a more interpretable way. Okay, so it was a way of regulating the problem is a physics-based way. So they called it, there's a lift augmented autoencoder. What we've done is added onto that producing pressure. So we're now predicting pressure and lift from that latent state. So that does the same. It organizes the latent space, but it does something very useful for us because that's our observation operator right there. So we're going to be using this latent state as this latent space, and we're going to do all of our assimilation, all of our data, our flow estimation in the latent space because it's nice and low dimensional. And then all the things I need to do filtering, an observation operator and a forecast operator, they're going to be learned operators as well. And that's one of those two right there. Okay. So this is an example. Actually, it is a plot from Kai's paper. They used a three-dimensional latent space. I mean, it's kind of incredible to think that you could take a flow field, which is hundreds of thousands of dimensions in size, right? That's the dimensionality of that flow field, and reduce it to 3 numbers, right? I just still find that incredible. And because all the information about reconstructing it is in those weights, right? So this latent space is very low dimensional, and there's even a lower dimensionality even in there because there's kind of a manifold of states that things tend to lie on here, okay? So these are different angles of attack of a wing, 20, 30, 40, 50, 60, and they're sort of in between there. There's some, your eye sort of reconstructs a manifold in there. So it's a very low dimensional space to work in. We're not going to use a 3-dimensional latent space. Ours is going to be a little bit larger. I think we use a 10-dimensional latent space. And the reason is because it makes it a bit more observable. So we're trying to make it more observable, but it also makes it, the reconstruction loss is a little bit improved as well by having a little bigger dimension. So there's a bit of a balancing act there. So it's a little bit of a trial and error that we found that out. Okay, so we're going to do all our assimilation in there. Okay, so as I mentioned, we need 2 ingredients for our filtering. One is a forecast model. Okay, so the forecast model will take the previous latent state and predict what the next latent state is, all right? And then the observation operator will take that latent state and predict the pressure, okay? And the lift as well, but pressure is the more important one. And so those are the two ingredients I need for a filtering architecture. Okay, so those become the elements of our ensemble Kalman filter, or low rank ensemble Kalman filter. So here's the training that we're going to do. We're going to take several different angles of attack and with pressure sensors. This is a NAC airfoil, very low Reynolds number. It's a very simple flow, but it's got enough complexity to be interesting. So these gusts here, like the ones I showed before, there are these vortex dipoles hitting this wing at different angles, different strengths, different locations, and we're going to just collect data. Okay, so I'm going to just go right to the results here. So this is at 20 degrees, and now I'm showing you results now on unseen data. This is not part of the training. This is actually the deploying it on new cases. So at 20 degrees angle of attack, the lift actually is fairly constant without a gust. So the lift would just be right there, if there was no gust. But the gust produces a really large deviation from that nominal angle, nominal lift, and so the estimate actually does a really good job of getting that. So now my ensemble Kalman filter with neural network operators actually does a very good job of latching onto that, and the uncertainty is pretty low on that. So this is what that uncertainty looks like back on vorticity. So this is the ensemble mean. This is the true vorticity. Okay, so that was the case that it was that underlies all this thing, but we never know it, right? But we, in this case, we're going to play God and assume we know it, okay? But this is what we actually measured. We got this ensemble mean, and this is the uncertainty. This is where we're most confused about that flow field. So there's a few places that we're confused about where the gust is right there, and we're confused a little bit about some of the passage of that gust past the wing as it's sort of inducing vortex shedding and so on. And it actually even thinks at this point there's maybe some gusts still lingering ahead, so it's a little confused there. But these are very small amounts of uncertainty compared to the fact that generally the flow field is predicted very well in this case for what we have. We just have sensors, right? And so this is another example at 60 degrees where the flow field without a gust is now periodic. So if there was no gust, it would just be this periodic trajectory going back and forth, up and down, okay? And then the gust hits at some point in the phase of that cycle, and that's the passage of the gust there you can see. So again, the lift is predicted very well. There's a little bit more uncertainty in this case. And actually the ensemble mean for the vorticity is a little better than the previous case, I think. But there's there's still some uncertainty about where that vortex, that trailing edge vortex is here. But again, this is just like showing a shift in location, right? So it kind of tends to amplify that uncertainty just by not exactly knowing where this vortex is, for example, right? All right, so it's revealing a lot of the things that we might be uncertain about, but we still feel pretty good about that. What's interesting is to sort of dig into that ensemble Kalman filter and figure out what was going on sort of behind the scenes while it was doing that estimation. So this is at 60 degrees again. So remember, we're doing this low rank decomposition where we reduce the rank and we throw away the non-informative stuff. So even though there's a 10-dimensional space, actually the state rank stays between 6 and 7 always. And the measurement rank here, remember there's 11 sensors, but actually the measurement rank is only 5 or 6, which means it's not collecting that much information from the sensors compared to how many sensors there are, which raises an obvious question. Could we throw away sensors? Okay, and I'll answer that in a second. There's eigenvectors associated with those low rank modes. And so if you look at those eigenvectors, then they tell you about how the sensors are being weighted, okay? So for example, right at this instant here, then, and this is how the sensors are numbered here, just for your reference, then sensors near the trailing edge are not particularly highly weighted, but near the leading edge, not surprisingly, right? The leading edge is where all the action is here. Those sensors are being pretty heavily weighted, right? And then mode 2 weights them a little differently. So remember, it's assembling its update from these modes. And mode 3 does things a little bit differently. So these are just different ways that it's assembling information from those sensors. But then mode 11 is one that we threw away. Mode 11 is like sort of more scattered assembly of sensor information, and it wasn't informative. It decided. Okay, so we threw that away. So it goes away. Okay. So I mentioned before, you know, since we have more sensors than modes that we're really using, we could start dropping some of these sensors. So what we did was, it's very easy to do that. We just raise the noise level on individual sensors and make them very untrustworthy. And so that's all we need to do to basically mimic it being dropped as a sensor. And so dropping sensor 2, right? Sensor 2 was near the trailing edge on the upper surface. We still do a pretty good job. Sensor 6 was a really important one, is right at the leading edge, and we still do a pretty good job there. Okay, so we're still doing it okay. And then we drop 3 of them actually. So this is as bold as Hania wanted to be. She didn't like, she was, I'm trying to get her to go further. Okay, just keep dropping sensors. And so she dropped 3 and still do a pretty good job there. Okay, so I'm at some point this is going to fail, right? Because we're going to have fewer sensors than states to estimate, and so this will probably start working poorly at some point. Okay, so I spent a lot of time talking about that. I'm going to talk a little bit less about the control part, which seems a little bit ironic since I started with that question. But there's so here there's a lot of things to talk about, but I find the estimation problem to be more interesting to dig into in many ways. So going back to this question, can we control this flow with sensor information alone and just pitch control? Okay, now we're going to go back to that question. Again, we're pitching about some point. We're going to pitch about the midport point for a while, and then we're going to switch that in a moment. Okay, so this is the sort of things that go into a reinforcement learning problem. You choose what you're going to observe. In this case, we're observing some information about the wing. Okay, but mostly it's pressure sensors. Okay. And we're going to just choose an angular acceleration. That's our action. Okay, action is going to be the pitch about that pivot point. The reward is basically like penalizing deviations from some reference lift. The reference lift here is 0. Okay, so we're penalizing lift that's not 0. Okay, and we're also penalizing rapid changes of action. We don't want to move things too quickly. And we're really penalizing things if the episode sort of goes off the rails in some way, like it does something weird. Okay. Okay. So those are the things we trained it on. Okay. Now I'm going to mention something here that I had that whole thing, you know, for the first 40 minutes or so of my presentation where I talked about we need to do flow estimation, right? Okay. Now here's where nominally you would plug in. So my policy here is finding an action given the state. Okay. And well, I know how to find the state because I know how to do flow estimation now. Great. So in the reinforcement learning community, this is really about what they call the belief state, like how, you know, what you believe to be the state's value. Okay. So this is where I always thought things would plug into here for the reinforcement learning part. Okay. But actually, Zheng, my student, spent, you know, quite a bit of time thinking about this on his own. And he said, well, what if we just learn a latent space from the pressure directly, right? So in other words, don't worry about the vorticity field. Just say, oh, I've got a bunch of sensor data over time. Let's try to learn some sort of low dimensional latent space for just pressure alone. And one valuable tool in that arsenal is the idea of what's called a transformer, which I'm sure many of you have heard of. It's become a pretty popular idea in the reinforcement, in the machine learning community. Transformers, I mean, this paper has been cited like 200,000 times now. It's kind of nuts. I mean, like, that's crazy. Like 200,000 papers on, oh my God. So this transformer, what it's doing, I mean, you know, some of it's a little black magic, but it is really taking time correlations between different elements of the history, right? So it's just comparing historical pressures with each other and looking for signal, right? Looking for traces of a signature in those sensors, right? Which is exactly what you want to do. You basically want to see if there's an event like a gust that hits, what you want it to do is look over the signal of pressure that it's gotten so far and find the signature of that gust, right? That's what you want. You don't necessarily need to reconstruct vorticity to do that. You just need to know that the signature lies in the pressure, right? So what Zheng did was he just built the idea on that transformer. And so I won't go into this architecture, but it's the same idea I showed before, just wrapped around differently. It takes an action and puts that into our environments, and the environment gives us back an observation and a reward. Okay, so this is using what's called the proximal policy optimization, which is a pretty standard tool now in the reinforcement learning community. One thing that we'll add to this is that we don't want to start from scratch. We want to start from something we already know works pretty well. And actually, linear control is a good starting point. So we should start with something we know how to do, just proportional control. Like the first thing you learn in your feedback control theory class is proportional control. Okay, so we're going to do proportional control, which says, given the lift's deviation from what we want it to be, let's set the action to be proportional to that. Okay. Okay, so let's pretend we're dumb and we don't do that. Okay, so this is what the training looks like without leveraging what we knew. So it takes a long time, lots of episodes and so on. But if we start from pre-training with that linear controller, actually we're almost there already. In fact, it does very little extra. So I'm zooming in here. It takes like only a few trial and error episodes to converge, which is very nice. So Zheqiang tried a few different proportionality constants, and the proportional control is in there. Okay, so now what we're doing now is we're going to try to compare. Did we do any better than linear control? Okay, well, if I stopped here, then you would say, no, this is a waste of time. Reinforcement learning did not help us a bit because it's only a very slight improvement over classical control approach here. So that seems kind of ludicrous to spend all that effort trying to make it marginally better. But that's actually not what our goal is. Our goal is actually to make this work in these sort of indefinite sequences of strong gusts. Okay, so I'm going to show you what happens. For example, if we have 3 gusts in a row, each of them is leaving sort of a lasting impact on the wing. So there's this sort of residual effect as every gust passes, and these gusts sort of interact with each other then. Okay, so there's some important flow features to capture. And so we do a little better now by training on 3 gusts. Okay, so our training protocol now involves not just 1 gust, but 3 gusts. And then we can ask the question, well, are we good enough now to do n gusts, right? Like just keep hitting it with gusts. And the answer is yes. So the red line here is no control. So that just means the lift goes up and down because the gust is hitting it. And all of the curves here are different versions of control. Now, the best proportional control looks pretty good, except it's got some really serious wiggles here. So this is basically the action, the acceleration, jumping back and forth between positive and negative, because it's pretty dumb, okay? And it keeps going back and forth. There's a good reason for that I won't go into. But the yellow and the blue are what the reinforcement learning how to do. It basically found a much smoother trajectory to follow, and the lift is actually better. Okay, so it gets very low lift in that case. Okay, so what it's learning how to do is pretty simple. It's learning how to sort of slalom between the vortices that are hitting this and minimize the lift that way. It's a pretty simple thing in the end. Okay, now mid-chord pitching was pretty strong effort. Actually, people have known in aerodynamics for a long time that pitching about the quarter chord is a better idea. Okay, so we'll pitch about that quarter chord. So we'll train it again. Here we are going to start from no knowledge at all. We're not starting from any linear controller. It takes a little while to converge. And then we'll train it on 3 gusts. So we're going to do what's called transfer learning here and start with that and train it again on 3 gusts. It converges. It has to unlearn some things here before it gets started, but it does a pretty good job. Okay, but we're still trying to work out better training protocols. And then we apply that to n gusts. Okay, so now it learns how to do the same thing, but with a lot less effort. So what you notice here is that if you remember the curve that I showed you a few slides ago, the action was going back and forth with much larger amplitude. But now at a quarter chord pitching, it uses much less energy to basically do the same thing. And that's because it learned about added mass, right? So added mass was a feature it couldn't exploit very well before. But because it's pitching about this point, then there's a sort of a heaving part of this element. So this thing is sort of heaving up and down and able to push on the flow. And the inertial reaction from the flow provides this extra benefit of lift. In fact, if you unwrap this, you'll find out that for every gust disturbance to the lift, the action produces an added mass, one that's sort of equal and opposite, and sort of learning to cancel that out with added mass. So it learned about, you know, that on its own. Okay, so it worked okay. So it's, you know, it's satisfying to look at after the fact, but we're putting very little guidance into this, right? So in some sense, it's still a little frustrating to me. But reinforcement learning eventually works. And it's just, you know, being okay with that. So the conclusions I have are, I just want to emphasize this fact, and I think this is, you know, speaking to the choir here. The probabilistic view of flow estimation is a very powerful toolbox, and I can't state that strongly enough, because it gives us all kinds of tools to do things we want to do. And I think that, you know, it tends to be forgotten sometimes in the sort of machine learning community. But I think that there's, you know, adding things like Kalman filters with neural networks is sort of a nice combination of tools. Okay, so that's been very useful. I love vortex models, but they provide, you know, some roadblocks that got in our way. So now we're using these autoencoders to great advantage, I think. And so, you know, the reinforcement learning, I think we're still trying to merge these two ideas together, right? So how we can do a better job of leveraging what we learned about flow estimation, but you know, they still work on their own. Okay, that's it.
All right, thank you, Jeff. Are there any questions? Zoom or?
Yeah.
Have you taken a look at other methods or other ways of control, like besides just like rotating the wing?
Oh, yeah, I mean, you ask a very natural question. I mean, pitch control is not something you generally use, except you do it on like wind turbine blades and rotorcraft. That's the only place where pitch control is actually used, but like on an aircraft, you don't do pitch control, right? You use flaps, right? Or you, in more exotic ones, you might use some pulse blowing and suction, but so yes, the answer is we're obviously meaning to look at that. In fact, our next target problem is a delta wing aircraft with flaps. Okay, so that's a much more complicated problem. We're easing into that because it's 3D, high Reynolds number, complicated geometry, and I just showed you like the exact opposite of that, right? Which is low Reynolds number, simple geometry, and low complexity, right? So. Oh, there's a question online. How will this generalize 3D flows? Yes. Yeah. Well, it'll generalize fine. I mean, we will have to maybe. So the challenge is resources, right? I mean, trying to train an autoencoder. So Sam's group, for example, my colleague at UCLA, his group has been training autoencoders on flows past like a, you know, canonical flow past a cylinder, three-dimensional flow past a cylinder. Or three-dimensional flows past airfoils. They've had success with that, so that we know we can train the latent space. Okay, once we have the latent space, actually it becomes a lot easier, right? Everything after that is like trivially simple. I mean, it's a very low dimensional space. All the training is the bottleneck. So we're just trying to minimize that to the extent possible before we march into that. But there's no reason to believe it won't work.
So sorry, there is one question
Oh.
from Yan Diet, but he says, thanks for the presentation. Can you please go back to an earlier slide with non-linear?
Oh,
Thanks.
yeah. Non-linear, okay. Maybe, I'm just gonna guess where he wants it to be. Here. There? That many ones?
Can you send a message in on the chat? Is this the
Maybe in the
one?
meantime, we can have another question here.
Yeah, so I guess while that's pending, I was curious, I realize it's kind of apples and oranges because you're trying to do different things, but if you had to compare computational cost of doing the RL approach
Right.
versus like, okay, I'm gonna learn a model in the latent
Yeah.
space and then
Right.
kind of
Yes,
work
exactly.
on the model.
Yeah.
What are your feelings there?
Yeah, I mean, so we had previous version of our reinforcement learning, we did it all in the latent space. Okay, I didn't show those results here because it seemed like that was the way to do things. So we learned the latent space and then we learned how to do all the dynamics in there and learn about policies that would work in there. So that actually worked really well, because then you could retrain your policy in seconds. It was very nice. So I'm still not, we might go back to that idea, right? And there it's, then all the training costs are just the same training costs that we just dealt with
Oh,
here,
because like
right?
once you're, so basically to do the training of the policy, you're using the learned
Yeah,
model in the.
yeah, exactly. So the training is like so easy, right? All the trial and error, as long as you trust your dynamical model, right? And the and all of the physics are properly captured in that latent space, then it's pretty easy to do exploratory reinforcement learning in there. So that seems like, to me, probably the best path forward, I think, for fluid dynamics, probably.
Maybe one follow-up. So the model in the data assimilation side of the talk,
Uh-huh.
where you're learning the model in the latent space, and
Yeah,
okay, I guess like we're discussing, there's no guarantee that the dynamics really are Markovian.
yeah, right. Mhm.
Have you guys experimented with sort of then taking a model that predicts like step k plus one
Mhm.
based on, you know, some memory
Sure,
window
yeah.
of past?
So in fact, the reinforcement learning one, we use long short-term memory, a pretty standard toolbox from machine, RNNs, recurrent neural networks. So that worked fine, right? I mean, you can encode everything you want into a recurrent neural network. And so, yeah, that works fine for what we needed at the time, which is to learn enough about the dynamics and predict those dynamics so that we could predict what would happen if we tried different actions, right? And then we said, well, that's not very desirable from a flow estimation standpoint. We want that Markovian feature. So we said, let's go back to something, where it's a simple update model, right? But yeah, it's not Markovian in that latent space, because there is the tendency for trajectories to cross, and that means that things are not unique, right? Yeah. So there's some uncertainty about that. Yeah. I will go back to the question, I think.
Right. So so this person asked, Yan asked if you can elaborate on this nonlinear.
Oh, yeah, okay, right. So the nonlinearity that we're talking about here is that the flow states influence on sensors, right? And I mentioned, for example, in fluid dynamics, that if our sensors are pressure sensors, which is the case in this talk, then they're going to depend nonlinearly on velocity. And so that's just a simple way of understanding that. It also, there's nonlinearity that comes in other ways sometimes. For example, in this problem here, sorry, I'm fast forward. Yeah, this one here, there's two forms of nonlinearity in this case with these vortex elements. Not only does pressure depend nonlinearly on velocity, it also depends nonlinearly on the location as well, right, of those vortices. So there's different ways that nonlinearity manifests itself in these fluid dynamics problems. But is there a follow-on question, maybe?
It's learning.
Yeah,
I
right.
think not yet.
Thanks for the great talk. For the first part on flow estimation,
Mhm.
you talk about the redundance of certain sensors.
Right.
And obviously I'm also interested in okay, how many can you get down to like 3, 2, what
Sure.
have you. But
Yeah.
do you think that the actual redundance is in the physics, or is it just that the neural network ignores the, let's say high frequency or other like spurious oscillations that would make it higher rank?
Oh, yeah, there's no neural network in this one.
No. Sorry,
Oh, you mean
the next one.
Oh, I see what you're saying. Yeah. Now I understand what your question is. Yeah. Right. So I think that what I think is happening here is that okay, that's an important question. Okay. So what we want to be able to do is I'd like to say definitively that this is reflecting physics here, right? Okay. Which I 90% believe is true. Okay. But there's that 10% which is like, okay, maybe as you said, the neural network is just missing some information, right? And so we're just finding out the limits of what that neural network is able to encapsulate, right? So what I'd love to be able to do is connect this picture with these modes with what I showed you with that picture of vortices out in space with pressure sensors, right? And to some extent I can, but it's more loose. Okay, so for example, we know that if I have, and this actually went into my paper with Yusuf here, if we have a vortex out in space and a bunch of sensors, these modes actually are a multipole expansion of that vortex. Okay, so it means that actually it's just unwrapping the solution of Poisson's equation. Okay, so it's actually giving us an insightful view of something we would get, you know, by other means. Okay, so that's an encouraging thing. What I'd like to be able to do is say that that's sort of what we're seeing here as well, that these are things that could come from, say, a multi-pole expansion of all that vorticity, for example, on the pressure sensors around this wing. Okay, I haven't proven that, so it's more I'm going to say boldly that's exactly what they are, but that's not maybe true. Okay, so yeah, if we're trying to minimize the neural network's sort of impact on this. Yeah, thank you. Yeah, good question.
All right, maybe a last question.
Sure. So you've done this whole experiment with these sensors that are sort of 1D, so it's pressure sensors around the wing. Have you thought more about sort of like more practical sensors, like I guess in this case, a 3-hole probe since it's 2D, but sensors that you could sort of implement on like an actual aircraft?
Yeah, right. So yeah, exactly. So more practical sensors would be obviously useful. Now, we did some work about a decade ago on a different problem. So imagine a formation of aircraft, okay, and you have a leader aircraft and a trailing aircraft, and you want this trailing aircraft to sort of position itself to get the best benefit of drag reduction, right? So that's what birds do, for example, and we can do that with aircraft too. So what we wanted to do was do that autonomously, okay? So we were relying on sensors on that trailing aircraft, and this was a work that was sponsored by Boeing and DARPA, and Boeing said, we're not putting any new sensors on this aircraft. And they were very adamant about that. So we said, okay, well, we'll figure out what we can do. So we said, well, have some angle of attack sensors along the wing, which actually was more than they had. But we said, okay, we'll just a few more. Okay, so we used angle of attack sensors, and that was enough to infer the location of the trailing aircraft's or the leading aircraft's wake. All right, so we were able to detect basically, from our model, we had an observation model of what those angle of attack sensors should see based on proximity of another vortex. So my answer is that we've done other sensors, okay, and of course there's other sensors we'll try to do. We want to also fold this into the flight dynamics too, and look at IMUs and that sort of thing, right? Yeah, it's a good question.
All right. On that note, let's thank Jeff again.